Taiwan sits directly on the Pacific Ring of Fire, a tectonic danger zone battered by several violent typhoons every single year, constantly threatening to tear human infrastructure apart. For decades, the primary rule of structural engineering was simple: keep heavy, tall buildings far away from active fault lines. But in the late 1990s, Taiwan proposed a 101-story financial center that deliberately ignored that rule, aiming to construct the tallest building in the world directly on a seismic zone. The immediate danger was entirely underground. The chosen site was the Taipei Basin, an ancient dried-up lakebed composed of soft clay. Building a half-kilometer tower on clay is like balancing a brick on a mattress. Before we break down the engineering that made this possible, subscribe and hit the bell icon so you don't miss our upcoming deep dives. This diagram illustrates what happens when seismic waves travel through this ground. Vibrations rapidly increase water pressure in the soft soil, stripping its load-bearing capacity and turning solid earth into a turbulent liquid, a process known as soil liquefaction. Designers had to anchor a 700,000-ton tower into earth that could liquefy at any moment, while simultaneously ensuring the upper floors could withstand hurricane-force winds. To secure the building, engineers first had to bypass the treacherous clay basin. This cross-section shows the subterranean solution. Engineers drove 380 concrete and steel piles 80 meters deep through the soft soil, embedding firmly into dense bedrock. Those vertical piles are capped with a 4.7-meter thick concrete raft, safely distributing the tower's immense weight. With the ground secured, the focus shifted upward. A standard rigid steel skyscraper frame is highly susceptible to shattering under the extreme high-frequency shaking of a Taiwanese earthquake. Architects looked to a 5,000-year-old plant for the solution: bamboo. Bamboo is highly flexible, bending in violent storms but rarely breaking due to its segmented nodes. This diagram highlights how that biological concept translates to structural engineering. The tower is built in 8 distinct modules. At the junction of each module, horizontal outrigger trusses grip the exterior megacolumns. By locking a solid bedrock foundation to a segmented, flexible superstructure, the engineers created a system capable of safely absorbing and dissipating seismic energy. This photo shows the tower on March 31, 2002, when it was only 47 stories tall. That day, a 6.8 magnitude earthquake struck the city. The shaking was violent enough to snap 2 construction cranes stationed at the peak, plummeting to the streets below. 5 people lost their lives, and the project was halted immediately for a safety review. When inspectors evaluated the exposed steel skeleton, they found 0 cracks in the core structure. The outriggers and megacolumns had absorbed the shockwave exactly as designed. Surviving an earthquake was only half the battle. This diagram shows the threat to the summit: vortex shedding. Typhoon winds hit flat surfaces, separating into violent alternating whirlpools that push the building. Engineers disrupted this by cutting double-stepped sawtooth corners into the exterior, forcing wind to flow smoothly past. To handle the remaining wind force, they installed a 726-ton tuned mass damper, a giant steel pendulum suspended near the summit. When a typhoon pushes the tower to the right, the massive sphere swings to the left. Hydraulic shock absorbers catch the pendulum's energy and dissipate it as heat, canceling the building's sway. Instead of hiding this system, the architects left it exposed. They used gravity to fight the wind, ensuring the steel structure wouldn't suffer from long-term fatigue. The final challenge was getting thousands of people to the top efficiently. Engineers installed aerodynamic, bullet-shaped elevator cabins utilizing atmospheric pressure control, rocketing passengers upward at 60 kilometers per hour. On New Year's Eve 2004, officials marked the grand opening of the building as it officially claimed the title of the world's tallest. While the Burj Khalifa, seen here, eventually took the height record in 2010, Taipei 101 pivoted its strategy toward environmental performance. In 2011, following an overhaul of its water recycling and HVAC systems, it earned a LEED Platinum certification, making it the tallest and largest green building in the world at the time. Today, the tower defines the Taipei skyline, acting as a laboratory for engineers who still study how the massive golden pendulum keeps the structure stable. Taipei 101 demonstrated that mega-tall buildings cannot rely purely on rigid mass. To survive the harshest forces on the planet, they must be designed to bend with the storm.